Okay, think back to your high school physics class for a second. You were likely taught a very foundational truth, right? That the hydrogen nucleus is incredibly simple. It's just a solitary proton, a single positively charged building block of the universe. But what if that simple, solitary dot we've all been picturing is actually hiding something way more complex? What if the foundational building block of modern high-energy physics is in fact a master of disguise?
Welcome to this explainer. Today, we're going to impartially unpack a fascinating and, frankly, highly controversial theoretical paper centered on the Riemann atomic model, or RAM for short. We are going to explore this framework to see if, according to these authors, particle physics has basically been fooled by a cosmic magic trick. It's a theory that challenges the very core of how we understand the atomic world. So, let's dive right in. Here's our roadmap for today. 1. The bare proton assumption. 2. Inside the RAM nucleus. 3. The charge illusion. 4. Collider consequences. And 5. Rethinking high-energy physics.
Section 1. The bare proton assumption. For decades now, conventional accelerator practice has operated on a very specific assumption. We treat the hydrogen nucleus as a solitary proton. We strip away the electrons, accelerate those positive ions, and describe the output as a pure proton beam. But the RAM perspective argues that this description is fundamentally incomplete. According to RAM, the hydrogen nucleus is actually not a single elementary fermion at all. Instead, it's a closed, tightly bound composite. Section 2. Inside the RAM nucleus. If the hydrogen nucleus is not just a single particle like we've always assumed, what exactly is inside it? Well, RAM pictures a tightly bound, charge-neutral composite made up of 4 distinct constituents. According to the model, the ground-state hydrogen nucleus actually contains a proton, a neutron, an antineutron, and a bound Higgs-like boson, all arranged in this closed, self-shielding configuration. Let's zoom in on 2 of those pieces for a moment, the neutron and the antineutron. According to the paper, this pair forms what they call a virtual neutral core. And the crucial point here is that this core is permanently present within the nucleus, yet it is never free. Because the internal charges and baryon numbers cancel each other out so perfectly, the entire composite stays completely stable under ordinary laboratory conditions. And that brings us to the final piece of the puzzle, the bound Higgs-like boson. Now, quick clarification, RAM states this is not the free Higgs boson of the standard model that you might have heard about in the news. It's actually a bound, low-energy mode. It acts almost like a set of discrete bricks that quantize the local vacuum energy density inside the nuclear volume. This bound boson attaches to the nuclear energy store lattice, stabilizes the trad, and most importantly, it fixes the radius of the nucleus. Section 3. The charge illusion. Now, this brings up a truly mind-bending question. If there is all this neutral, hidden stuff packed inside, a neutron, an antineutron, a stabilizing boson, why do our instruments only ever measure a single positive charge? To understand this magic trick, we have to look at the nuclear Gaussian surface. You can think of this surface as a closed box, the outer topological boundary enclosing all of those complex constituents. To an exterior observer, this boundary completely hides the internal degrees of freedom, so the observer just registers a bare proton, while mathematically, the internal charges just effectively vanish from the outside perspective. Let's break down how this creates an actual illusion. Step 1. Imagine the nucleus totally at rest. In its rest frame, the Gaussian surface is perfectly spherically symmetric, which means all those internal multipoles cancel out perfectly. Step 2. Acceleration. When the nucleus moves at relativistic velocities, like it does in a particle accelerator, the surface becomes Lorentz contracted along the direction of the boost. And step 3, the illusion. That contraction actually breaks the perfect cancellation, and what is left behind in the laboratory frame is a residual monopole of a +1 positive charge. RAM calls this specific phenomenon the relativistic plane of direction effect. What you really need to take away from this is that the bare proton charge we have been measuring all these years is, according to this model, just a frame-dependent projection. It is not an intrinsic elementary property of a single particle. The positive charge is literally an illusion generated by the speed and the shape of the boundary projecting it. Section 4. Collider consequences. So what happens when we take these complex, hidden packages and smash them together at multi-TeV energies? Well, if RAM is correct, every single proton beam actually contains these bound neutron-antineutron pairs and Higgs-like modes. When we collide them, we might be exciting or partially dissociating that internal structure. Because of this, RAM predicts a few observable consequences that standard models just can't account for: anomalous productions of neutron-rich final states, an excess of missing energy, subtle shifts in the effective center of mass energy because some of it is tied up in internal binding, and non-standard measurements of the proton radius.
The authors argue this point really forcefully. If you treat the beam as a pure proton beam, you are discarding all these internal degrees of freedom. And once the beam energy exceeds the binding scale of that nuclear Gaussian surface, ignoring those constituents becomes a massive, uncontrolled approximation. You're basically trying to do math with an incomplete equation.
Section 5. Rethinking high-energy physics. If this theoretical framework holds any water at all, it could have paradigm-shifting implications for machines like the Large Hadron Collider. Over the years, there have been these systematic discrepancies between high-precision LHC measurements and the expectations of the standard model. According to Rom, these tiny anomalies might not be errors. They might actually be the very first experimental signatures of this hidden composite structure revealing itself in the collider.
To really sum up the gravity of this, let's look at a direct quote from the paper. If the model is ultimately confirmed, a substantial fraction of the interpretive framework used in modern Hadron Collider physics will require revision. Just think about that for a second. We would have to revise an entire framework of physics that has been trusted since the very first hydrogen ion sources were built. Everything we thought we knew about the simplest nucleus would have to be completely reevaluated. Which leaves us with this final, pretty provocative thought for today's explainer. If the standard model is incomplete and the solitary proton itself is just an illusion, masking a complex, tightly bound universe of its own, what other hidden structures are waiting to be unmasked? What else has been present, completely unnoticed, right in front of us this whole time?